It's a great pleasure. It's a great pleasure for me to introduce Jugal Verma. Jugal got his degree at Purdue University under the direction of Bill Heinze, and he had some short-term positions at the University of Kansas and also at Louisiana State. And after that, he spent most of his career at IIT Bombay. And Jugal had a great influence on many young people, and he did great things for commutative algebra and mathematics in general in India and beyond. And now he is a visiting professor at IIT Gandhinagar. And today he's going to talk on adjoints of powers of ideals in regular domains. Please, Jugal.
Yeah. So thank you, Bernd, for this invitation, and also thanks to Carl for organizing this seminar. It's a great way to connect with everyone from so many decades ago, and I'm glad to see Craig, one of my great teachers at Purdue, here. Although people introduced me by saying that I was a student of Bill Heinze, but unofficially, Craig was also my advisor because much of my work is influenced by Craig's papers and many people over here who are present. So it's a pleasure to speak in this Fellowship of the Ring seminar. So I'm going to speak about adjoints of ideals in regular domains. This is an interesting topic because it connects well with what I learned from Craig. Craig gave a course at Purdue on complete ideals, Zariski's theory of complete ideals. It was first an informal course. I remember he was not able to walk, but he lectured for the whole semester on Zariski's theory of complete ideals. This was, I think, 85 or 86. And then he wrote his excellent survey paper on complete ideals in the proceedings of MSRI workshop in 1987. It was a micro program in commutative algebra. And it was great fun to learn these things from Craig. And it is an inspiring theory full of excellent things. And this is one aspect of complete ideals. And there are problems in this area which I will talk about. So the talk is divided into two parts. First part is for people who may not know these things, reductions and integral closure of ideals, and a brief overview of Zariski-Lipman theory of complete ideals in regular local rings. The main technique that we use is the Hoskin-Deligne formula for co-length of a complete M primary ideal in a two-dimensional regular local ring. This formula is valid in higher dimensions with certain variations, which was done by Claire. And this could be useful to understand adjoints in higher dimensional regular local rings, but this is something that I'm exploring with various people. I will introduce joint reductions and mixed multiplicities of ideals in local rings. This is basically because there is a subadditivity problem of adjoint ideals or their analogs, which are called test ideals and multiplier ideals. The subadditivity problem has many interesting applications like uniform behavior of symbolic powers. But to approach the subadditivity problem, I propose to use joint reductions and mixed multiplicities. Because whenever you deal with a family of ideals, these are good techniques to understand in that setting. I will show how adjoints improve the con-Skoda theorem. And so this is the part of the preliminaries for this lecture. Part 2 will present new results, adjoints of ideals in regular domains. And the main conjecture that I want to focus is Lipman's conjecture about adjoints. This is more or less known for all good rings by work of Dale. There is an appendix in a 1994 paper of Lipman where Dale proved a vanishing theorem. And the vanishing theorem for certain local rings does imply Lipman's conjecture. But as far as I know, Lipman's conjecture is open for arbitrary regular domains. Unified proof of Lipman's conjecture and subadditivity. So these are two different conjectures, subadditivity of adjoints and Lipman's conjecture. But using mixed multiplicities, we can actually combine them, at least in dimension 2, and probably in higher dimension using some sort of assumptions about singularities of the normalized Riesz algebra. If there is time, I will also present adjoints of monomial ideals and how adjoints of monomial ideals are connected to coefficients of normal Hilbert polynomials. So this is the plan. Let me begin. So you have two ideals, I and J. Just a minute. I need to remove these pictures. Yeah. So take two ideals, I and J, in a commutative ring. If J is contained in I and Jin is In plus 1 for some n, then J is called a reduction of I. Yeah. Smallest reductions are called minimal reductions of I, and if the residue field of a local ring is infinite, all minimal reductions require same number of generators, and that is called the analytic spread of I. The reduction number is the smallest n, so that the equation Jin equal to In plus 1 is true. Then we have the concept of integral elements. Take a commutative ring, I is an ideal. An element in R is called integral over I if there exist elements ai in the ith power of I, so that A satisfies a monic polynomial with these coefficients. The integral closure is the collection of all elements which are integral over I, and by definition it is contained in the radical of I. So if I happens to be a prime ideal or a radical ideal, then the integral closure is itself, and such ideals are called complete ideals. Northcott and Riesz, they in their 1954 paper, they connect reductions and integral closures, and they show that J is a reduction of I if and only if I is integral over J. And so Jarsky called such the ideals for which I bar is I as complete ideals. And here is a nice theorem which I learned in Craig's course first time. Product of two complete ideals in a two-dimensional regular local ring is complete, and there are many other results. This theorem of Jarsky in Jarsky-Samuel volume 2 appendix 5 is done for two-dimensional regular local rings, but the theorem actually goes back to 1938 paper of Jarsky, in which he does this whole theory of complete ideals in polynomial rings over a field of characteristics 0. All right, so let me give a quick overview of Jarsky-Lipman theory, because many of these concepts I will use in the later proofs. Let K be a field. Following Lipman, we use Greek letters, alpha, beta, gamma, for regular local rings of dimension at least 2, all contained in the quotient field of a two-dimensional regular local ring, alpha. For x belonging to alpha, we define the order valuation, order of x equal to maximum of n, so that x is in nth power of maximal ideal of alpha. We define quadratic transform of a local ring. The quadratic transform looks like alpha adjoined with all the fractions in m alpha over x, and we localize at a prime ideal. The prime ideal should contract to maximal ideal of alpha. So such local rings, one can show that they are regular local rings, and we say they birationally dominate the given regular local ring alpha. So the quotient field consists of all kinds of regular local rings, and so it is desirable to have some kind of structure theorem for such two-dimensional regular local ring, and the quadratic transforms give this structure theorem. And in this connection, we need this concept of infinitely near points. So we say a point beta. So points are used to denote regular local rings. So a point beta is infinitely near to alpha, and we write alpha precedes beta if there is a sequence of points alpha 0 contained in alpha 1 contained in alpha n equal to beta, such that each alpha I plus 1 is a quadratic transform of alpha I for all these i's. So by taking quadratic transform of a two-dimensional regular local ring, we obtain another two-dimensional regular local ring, and we can continue this process. Uh, if we are given such a beta which is birationally dominating alpha, and if this beta can be obtained from alpha by a sequence of quadratic transforms, then this sequence is unique. But in dimension 2 regular local ring, such a sequence will actually exist. So this is a theorem of Abhyankar from 1956 in his paper on valuation rings. So take a two-dimensional regular local ring with fraction field K and as a two-dimensional regular local ring that birationally dominates R. So its maximal ideal contracts to the maximal ideal of R. Then there are uniquely determined two-dimensional regular local ring, R contained in R1, contained in R2, and terminating at Rn, so that each Ri is a quadratic transform of the preceding Ri minus 1. And this is a unique sequence, and this theorem is extremely useful to prove many results about complete ideals. In particular, we have a formula due to Hoskin and Deligne for co-length of a complete ideal. For this, I need some notion of strict transforms. Take I to be an ideal of alpha and beta infinitely near point to alpha. Then the extension of I to beta factors as x to the r times I beta for some minimal generator of alpha. And r is the alpha order of I, so it is the maximum power of m alpha which contains I. The ideal I beta is called the strict transform. So if dimension is 2, the strict transform will be beta or an ideal which is primary for the unique maximal ideal of beta. A point basis is the set of all the orders of I beta where beta is birationally dominating alpha. So given an ideal, we construct this collection of non-negative integers. And this collection of non-negative integers somehow reveals many properties of the ideal I. If order of I beta is not 0, then beta is called a base point of I. So these terminologies, they come from algebraic geometry because Zariski in his 1938 paper says that he is constructing this theory to study complete linear systems on smooth curves. And somehow this is the arithmetic data which comes out of linear systems of curves. A non-zero ideal is called finitely supported if I has finitely many base points. This is a terminology due to Lipman. Lipman wanted to somehow restore theory of complete ideals from dimension 2 to higher dimension, and he came up with this concept of finitely supported ideals. In dimension 2, all m primary ideals are finitely supported. But in higher dimension, this is not the case. For example, there is an ideal in a paper of Craig and Sam, which on normal ideals in regular rings, where they construct an ideal, complete ideal in dimension 3 polynomial ring, so that its associated graded ring is not Cohn-Macaulay, and that ideal is also not finitely supported. It is a bit difficult to recognize which ideals are finitely supported and which are not. But that ideal in the paper of Craig and Sam is a good example of a finitely supported normal ideals whose Rees algebra is not Cohn-Macaulay. This is in contrast to what happens in dimension 2. In dimension 2, the Rees algebra of a complete ideal, the associated graded ring of complete ideal, they are both Cohn-Macaulay. So here is one result to be observed, that if beta dominates alpha, then the base points of I, the strict transform of I in beta, are simply the orders of I gamma, where gamma dominates beta. For two non-zero alpha ideals, the base point of I times j is simply the sum of the base point of I and base point of j. And the two base point sets of I and j are equal if and only if I and j have equal integral closure. Here is the formula of Hoskin-Deligne from Hoskin proved this in 1955, and Deligne proved this independently of Hoskin in 1973. And actually, there is a proof due to Rees also in his paper on pseudo-rational local rings. And Rees actually does not refer to Hoskin or Deligne. So I believe that Rees also found this independently. But by then, the formula was well known. Take a two-dimensional regular local ring. I is a complete M primary ideal. Then the co-length can be obtained from the set of base points. So look at the set of base points of I, and the base points involve order of I transform in S, where S is birationally dominating R. Take this binomial order of IS plus 1 choose 2 and multiply by the degree of this algebraic extension S mod MS over R mod M. So if R mod M is algebraically closed, this correction factor will not be there. And so this is a great formula which computes the core length of ideal in terms of the base points of S. And this formula implies that in a two-dimensional regular local ring, there are only finitely many base points because the length is finite. Now I introduce joint reductions and mixed multiplicities, which will be used to understand the subadditivity problem of adjoints. So take a Noetherian local ring of dimension d with infinite residue field. In this slide, I move away from dimension 2 regular local rings. Take an M primary ideal. The Hilbert function of I is the function length of R A mod In, and it is given by a polynomial for large n, and that is called the Hilbert polynomial. And we will write the Hilbert polynomial in terms of binomials in this form. E0I is called the multiplicity times the binomial x plus d minus 1 choose d, and then we write these in alternating form. E1 of I times x plus d minus 2 choose d minus 1, and the last coefficient is negative 1 to the power d times edi. Yeah. Now if you take another M primary ideal J, then Bhattacharya showed a similar property for the bivariate function, which is length of A mod I to the power u times j to the power nu. This function is also given by polynomial for large u and v, and this is called the Bhattacharya polynomial from 55. So there exists this polynomial with rational coefficients whose total degree is the dimension of the local ring, and the Bhattacharya function can be computed from this polynomial for large u and v. Later, this theorem of Bhattacharya was proved by Lipman and Tessier for arbitrary number of, finitely many ideals in a local ring. Yeah. So the terms of total degree d in this polynomial in two variables, they have this form 1 over d factorial times e0 I slash j u to the d, and the ith term is d choose I e I I j u to the power d minus I v I. And so therefore the role that multiplicity of an ideal plays in the bivariate situation is played by these d plus 1 mixed multiplicities. So in some sense, when you want to understand the interaction of two M primary ideals, these d plus 1 integers are very important to understand their interaction between them. And these are called mixed multiplicities of I, and this is a term due to Bernard Tessier, because these multiplicities, mixed multiplicities, can be realized in terms of system of parameters. Just like multiplicity of an ideal is multiplicity of a system of parameters. These are also multiplicities of certain system parameters where the ith mixed multiplicity EI is obtained by taking I general elements from J and D minus I general elements from I. And if that set of general elements form a system of parameters, then the mixed multiplicity EI is the multiplicity of that system of parameters. This was proved by Rees using joint reductions and Tessier by using general elements. And the converse of this theorem was proved by Irena in her thesis. So Rees proved these elementary facts in his paper. E0ij equal to EI and EDij is multiplicity of J. And if you take two positive numbers, U and V, then the Bhattacharya polynomial of this power product is really, you substitute VUT and VT in the Bhattacharya polynomial of I and J, and that gives us this formula. Okay, so look at the leading terms of P, U, T, V, T, and the leading term of the Bhattacharya polynomial of I, U, J, V. So for all positive integers, U and V, this is the formula for multiplicity of the power product. So all the mixed multiplicities, they go into understanding the multiplicity of power product. This is the theorem I talked about of Rees theorem. Take a quasi-unmixed local ring, J contained in I, be M primary ideals, then J and I have equal integral closure if and only if the multiplicity of I and J are equal. And we have corresponding theorem for mixed multiplicities. So first part is due to Rees and the converse was proved by Irena. So all the mixed multiplicities also have this multiplicity kind of theorem. Remember quasi-unmixed local ring? This is Nagata's terminology. So the completion is equidimensional. So dimension of the completion of A mod any minimal prime is equal to dimension of R. Then we say the ring is quasi-unmixed. So if J is contained in I is a minimal reduction, then it is easy to see that the multiplicity of two ideals are equal, but the converse requires quasi-unmixedness. Yeah. All right. So the motivation for introducing adjoints, of course, from Lipman's paper, the motivation could have been geometric, but at least he says that he wanted to give a new proof of con-Skoda theorem using adjoints. And at least in but the techniques of proving the con-Skoda theorem in Lipman's paper, 94 paper, are geometric, and I believe that many of those results now have purely algebraic proofs. So this is the starting of con-Skoda theorem by a question of Mather in 1971. So take a power series in D variables, which is not a unit, so f0 equal to 0, and take the Jacobian ideal, and we assume, I think we have to assume that f is an isolated, the origin is an isolated singularity. Then the question is there an s bigger than equal to 1 so that f to the s belongs to GF? So now this one can show this is true for s equal to 1 if f is a quasi-homogeneous power series. So a power series is called quasi-homogeneous if there are integral weights w1, w2, wn, so that f lambda w1 x1 lambda wn xn is lambda to the power d times f x1 up to xn. Yeah. So I don't see any videos. So if there are any questions, please feel free to stop me, and I can answer questions in the middle of the lecture too. So if f is quasi-homogeneous, then by Euler's theorem, d times the power series f is sum of the weights times xj times the partial derivative of f with respect to j, and this is certainly contained in jf. And therefore, Mather's question has a simple answer in this case. F itself is contained in Jacobian of F. If F is not quasi-homogeneous, one can show that F is actually contained in the integral closure of JF. Okay. This is the con-Skoda theorem. Take convergent power series ring for any non-zero D generated ideal. The integral closure of ID is contained in I. And that implies that the integral closure of ID plus n minus 1 is contained in In for all n. So it shows how big is integral closure. So it is eventually contained in In. So the powers of I and the integral closure of powers of I, they define linearly equivalent topologies. And this result says that if you take the normalized Riesz algebra of I, it is a finitely generated module over the Riesz algebra of I. Yeah. So using this fact, F belongs to the integral closure of the Jacobian, and therefore the dth power of F belongs to the dth power of the integral closure of the Jacobian, and that is contained by con-Skoda theorem. This is contained in JF. And therefore the original question, at least for the Jacobian ideal, it says that we have a uniform D. F to the D belongs to JF. Replace R with regular local ring and JF by arbitrary ideal. Do we have such a theorem? Yeah. So Lipman, Tessier, and later Lipman and Sathe, I think both papers appeared in 1981. They proved this theorem for regular local rings and pseudo-rational local rings. Take a d-dimensional pseudo-rational local ring or regular local ring and take any ideal of I, then the integral closure of I to the d plus n minus 1 power is contained in In. The non-trivial part here is the ID bar is contained in I. The other things just follow just by multiplying by I. So ID bar is contained in In, and therefore we have a uniform integer D. D is the dimension of R, which works for all ideals for this containment. Riesz and Sally gave a generalization of this result by using joint reductions. I will define that sometime. Take a d-dimensional regular local ring. Take x1 up to xd to be any joint reduction of m primary ideals, I1, I2, id. Then the integral closure of the product of these d ideals is contained in every joint reduction. You can take any d elements so that x1 is a sufficiently general element from I1, x2 is a sufficiently general element from I2, and so on. If they form a system.
The question.
Yeah.
So this D in this con-Skoda theorem.
Somebody has a.
Hello. Sir, I am Nina. Am I audible? Hello.
Hello?
Am I audible?
Yes, we hear you. We all hear
Nina
you.
Gupta talking.
Yes, we hear you.
Move to a different location.
No, I unmuted.
Hello? Yeah?
Yeah. So my question is this D in this con-Skoda's theorem is the number of generators.
No, it's the dimension of the ring. Is it? I mean, that.
Yeah, so uniform D will come from the dimension. But if I is n generated, then In bar is contained in I.
Okay.
Yeah.
Okay.
So if you are given an ideal M prime, you can find a minimal reduction which is generated by what is called the analytic spread of I, and analytic spread is bounded by the dimension, and so we get a uniform bound. And it's also one can state a result which depends on the number of generators of I also. Yeah.
Thank you.
Yeah, let me share the screen again because yeah. Yeah, can you see the screen now?
Yeah.
Okay. Yeah, maybe I have to. Yeah. Okay, so so Rees and Sally they generalized to products and proved that the I1, I2, ID bar is contained in every system of parameters, which is constructed from picking general elements from these ideals. Yeah. So now I'll define adjoints of ideals. Take a regular domain. This is the assumption made by Lipman. Take a regular domain with fraction field K. Evaluation
don't see your page, a new page.
You don't see the page?
No, still the old page.
So let me share once again.
Mm.
Yeah, do you see this?
Yes, yes.
Yeah. So this is ninth slide. Do you see the ninth slide?
Yes, yes, yes. We see it now. Yeah.
So adjoints of ideals in regular domain. So take a regular domain with fraction field K. A evaluation ring contained in K is called divisorial, or it's also called prime divisor by Nagata. If the maximal ideal of the evaluation ring intersects with R in P, and the transcendence degree of the residue field of the evaluation ring over the residue field at P is 1 less than the height. The set of such valuation rings, the divisorial valuation rings, is denoted by dr. Any divisorial valuation ring is localization of an affine R algebra. I think this was first noticed, proved in paper of Abenkar, that these valuation rings are DVRs, and they are finitely generated, localization of finitely generated R algebras. And due to this, one can write V as a localization of polynomial ring over R and get system of defining equations, and then use the Jacobian ideal for these defining equations. So I will not go into the definition. Jacobian ideal of V over R is well defined. Take a regular domain, I is an ideal. The adjoint of I is the complete ideal, which consists of elements from the quotient field, but they turn out to be elements in R, so that R times the Jacobian ideal of V over R is contained in IV. If you don't have the Jacobian ideal, it is simply the integral closure. And so Lipman used Jacobian ideal, some sort of coefficients for the equation. So R times the Jacobian ideal of V over R is contained in IV. Then this is adjoint of I, and one can see easily by the definition of integral closure in terms of valuation rings that the adjoint of I is containing the ideal I, and the way it is defined, it is a complete ideal because it is intersection of valuation ideals, and valuation ideals are contractions of principal ideals, and principal ideals are integrally closed in normal domains. So I is contained in the adjoint, and adjoint of I is integrally closed. So it will contain the integral closure. Yeah. So in the improvements of con-Skoda theorem, instead of the integral closure of powers, Lipman will replace them by adjoints of powers. And adjoints are often much smaller, much bigger ideal than the integral closure. So one gets a refinement of con-Skoda theorem and a new proof. So the adjoints were first looked at by Hoenicke and Swanson in the setting of two-dimensional regular local ring, where they proved a very interesting structure theorem. Take a complete M primary ideal of a two-dimensional regular local ring. And so this ideal has projective dimension 1, and therefore we have a minimal free resolution. And take the presentation matrix A, it's an n by n minus 1 matrix. And this matrix, using this matrix, they proved that the adjoint is generated by the sub-maximal minors of this matrix. Yeah. So this really gives a very effective way of computing the adjoints. From the definition, it is not clear how to calculate. We have to first calculate the Jacobian ideal, which requires understanding the equations and then intersect this. But this is really a very interesting way of computing the adjoint in terms of the sub-maximal binders of the presentation matrix. So here are some other formulas for adjoints. These are taken from Lipman's paper in 94. Take a two-dimensional regular local ring and take a minimal reduction of an ideal, M primary ideal I. Then the adjoint is J colon I. The adjoint of I is also equal to the colon ideal core of I in colon J. Core of I was introduced by Rees and Sally. The core of I is intersection of all minimal reductions. So J is one particular minimal reduction, but if you take intersection of all minimal reduction, this is contained in J, and then you take this colon ideal, what you get is the adjoint of I. Yeah. Here is another interesting formula due to Lipman. The quotient ring R mod the adjoint is the mathless dual of I mod J. So this says that one can calculate the co-length of adjoint using the length of I mod J. Adjoint of I is the unique complete ideal with point basis. The point basis of the adjoint is obtained by looking at the point basis of I, and wherever the point basis of I is positive, reduce it by 1, otherwise put it 0. So once you calculate the point basis of I, one can calculate the point basis of adjoint of I, and this is the unique ideal with this point basis. This theorem, this part D, is proved using part C. Lipman first proves part C and then proves part D to get the point basis of the adjoint. And once you have point basis of adjoint, one can calculate the co-length using the Hoskin-Deligne formula also. So this is the result of Lipman. Take a d-dimensional regular local ring, and I is a finitely supported ideal. So this is the concept for dimension at least 3. Take J to be d-generated reduction of I. Then J colon I is adjoint of I to the power d minus 1 plus J. And adjoint of I is the unique complete ideal with point basis, which is obtained in a similar way as in dimension 2. You take the point basis of I, and from the base points, order of the base points, subtract d minus 1. And if the order of I beta is less than d minus 1, put it 0. And so this is using the one can take the point basis of I and get the point basis of the adjoint of I. And as you saw in the previous slides, the point basis determines the integral closure. And right, so this formula part A, which is proved in Lipman's paper in 2007, is also found in the Olinda notes of Bernd Ulrich, where he gives a purely algebraic proof of this theorem. But in a restricted class, I think he has to assume that the normalized Riesz algebra has rational singularities. Yeah. So some results which are true in dimension 2 regular local ring, they seem to have some sort of analogs in higher dimensional. And one has to find the correct assumption on the singularities of the normal Riesz algebra. Here is a theorem of Howald from 2001. I think Howald was student of Irena, as far as I know. Take a polynomial ring over a field in d variables and take a monomial ideal.
He was a student at University of Michigan. He was a
I think
student.
Lazarsfeld, I think.
Yeah.
Okay. But his thesis was in New Mexico.
No, Mark Rhodes had a different calculation, not as streamlined as this.
Okay. All right. Okay. Yeah. So adjoint of I is again a monomial ideal. You begin a monomial ideal. Adjoint of I is again a monomial ideal. It has a very clean description. Adjoint of I is generated by monomials xu, so that when you add this vector u1, to the exponent vector, you get a lattice point in the interior of Newton polyhedron of I. So every monomial ideal has a Newton polyhedron. So you take all the exponent vectors of monomials in I and take the convex hull in d-dimensional Euclidean space, and then take the interior of this convex set, and that is the Newton polyhedron of I, interior of Newton polyhedron of I. Just a minute. Yeah. Right. So adjoint of I is again a monomial ideal, and it is generated by these monomials xu, so that u plus this vector 1, is a lattice point in the interior of Newton polyhedron of I. Yeah. So using this, for at least for monomial ideals in polynomial ring, one can calculate the adjoint. Now I come to Lipman's conjecture. Maybe this is a good time to take a break.
Yeah. So let's break for 5 minutes and we start again 21 after the hour.
Okay. Thank you. So can I start again?
Yeah.
So let me full screen. Okay, so in the second half, I want to talk about Lipman's conjecture about adjoints of ideals. This was made in 1994 paper of Lipman. Take an ideal of a regular domain. First some results which led to the conjecture. If the depth of the associated greater ring is at least 1, then the adjoint of I to the n plus L minus 1 is contained in IN, where L is the analytic spread of I. So this, if you forget about the depth of
Jugal,
GI plus,
we don't see the theorem. Only the assumption is there.
So if the depth of GI plus 1 is I is an ideal of regular domain, and depth of GI plus 1 is at least 1, then the adjoint of I to the n plus L minus 1 is contained in IN. Do you see that?
No, just the first line of the slide we see.
Maybe stop sharing and try sharing again.
Yeah, I'll stop sharing. Yeah, maybe the adjoint of I to the n plus L minus 1 is contained in IN for all n. This is a statement which generalizes Bryan's con-Skoda theorem in regular domains, because adjoint of I to the n plus L minus 1 contains the integral closure, because adjoint is always integrally closed. But with this assumption, Lipman proved this with assumption, and Bernd pointed out in his Olinda lectures that depth of GI plus is at least 1 is not really needed. Okay. So therefore, this is an improvement of the Bryan's con-Skoda theorem if you use the adjoints of ideals. Then Lipman conjectured the following. He wanted to have a more precise information about the adjoint rather than simply contained in IN. So I think this was sort of that goes along the line of results, which I think in one paper of Craig we find and Aberbach we find con-Skoda theorem with coefficients, and Lipman's conjecture gives a result which gives con-Skoda improvement of con-Skoda theorem with coefficients. This is made in 1994 paper. Take a regular local ring, and I is an ideal with analytic spread L. So he shifts to regular local rings because adjoints localize at maximal ideals. So it's enough to understand these in regular local rings. Suppose the analytic spread of the ideal is L, then for all n at least L minus 1, I times the adjoint of In is adjoint of In plus 1. So rather than a containment, this gives a precise relationship between the adjoint of In and adjoint of In plus 1. And so it says that if we can calculate adjoint of I square, adjoint of I to the L, we can calculate all the adjoints of later powers also. And so this could be very useful to compute the adjoints of powers of an ideal. Partial solutions of Lipman's conjecture are something like this. In dimension 2 regular local ring, Lipman proved his conjecture. Cutkosky, in the same paper, there is an appendix where he proves the Lipman's conjecture for rings which are essentially finite type over a field of characteristics 0. So let me ask Dale whether he has improvement over this, because this is proved long ago, almost 30 years ago.
Yeah, I haven't thought about it, but listening to your lecture, I'm very excited about all the things you're talking about. So maybe I'll try looking at it again. But I think once you go to characteristic P, everything gets really hard. So.
Right. But in characteristic P, of course, there are many vanishing theorems about test ideals, and if you prove something about test ideals, maybe things will follow for adjoints. Yeah. Anyway, so I hope this conjecture is open for arbitrary local rings. I met Lipman during the conference for Bill, and I asked him whether he knew anything more after 94 about his conjecture. And then his answer was, are people still interested in my conjecture? Yeah. So now then, Howald, I think Howald was a student of Irina in 2001.
No, Lazarsfeld.
Okay, Lazarsfeld. Okay. So take polynomial ring over a field and take a monomial ideal. Then this conjecture, because we have a description, concrete description of the adjoint, and one can use that to prove Lipman's conjecture for monomial ideals. Lipman came back to this theorem in 2007. He proved this for dimension 3 regular local rings, but the ideal should be finitely supported. Yeah. So what happens for complete ideals dimension 2 regular local ring could be true for finitely supported ideals. But I find it a bit hard to recognize which ideals are finitely supported. And Manoj Kumini and Masuti in 2021, they were exploring Ito's conjecture, but they also looked at Lipman's conjecture because it seems to be closely related. So take three-dimensional regular local ring so that the pros of the normalization of this algebra of I has pseudo-rational singularities, and the last coefficient of the normal Hilbert polynomial is 0. Then they proved this, and this is dimension 3. What happens in higher dimension? Maybe one of these days we will see Burns notes from Olinda where this will be proved in general. So in 2009 lecture notes for the Olinda conference, it is proved in the notes that if GI is Cohen-Macaulay, the associated graded ring of I is Cohen-Macaulay, or the extended Riesz algebra of I is Cohen-Macaulay, and the pros of the normalized Riesz algebra is rational singularities, then Lipman's conjecture is true. So in higher dimension, either you assume something more about the ideal, or impose restriction on the singularities of the normalized Riesz algebra. Then this conjecture seems to be valid. But what is surprising is that Dale's result assumes nothing about the singularities of the normalized Riesz algebra. Yeah, so Dale, do you have any comment on this?
Well, it's been a while since I've looked at this, but basically it's what I do is pretty simple, actually. It's just using Kodaira vanishing theorem. But the question that came to my mind right now is, let's say that you took R to be excellent, containing a field of characteristic 0. I would wonder if maybe it's true in that case too. But that's all I can really say at this moment. In fact, it might be it's very easy to prove it, and maybe not. I don't know.
Yeah. But you think that the condition on the pros of normalized Riesz algebra may be unnecessary for excellent rings?
Well, I don't know. I mean, the thing is that it's this Kodaira. I use Kodaira some variant of Kodaira vanishing, and that completely blows up in characteristic P. So,
I see.
that's the problem. I think in the rational singularities case, anyway, all the other variance results is quite nice, of course. So. But it may not be easy to give a complete solution to this.
Yeah. Okay, thank you. Yeah. So now I go to the other conjecture about subadditivity of adjoints. The subadditivity problem for adjoints is take ideals I and J of regular domain. Is it true that the adjoint of the product is contained in the product of the adjoints? So the adjoint ideal is connected to what are called multiplier ideals in characteristic 0 and test ideals in characteristic P. And I see that in many papers, this subadditivity problem is done for multiplier ideals and for test ideals for at least Gorenstein rings in a paper of Karen Smith. And Karen Smith says in somewhere that this is an important property because it leads to uniform behavior of symbolic powers. So that's an interesting connection of adjoints and symbolic powers. D. Melly and Lawrence Ein and Robert Rajersfeld in 2000, they proved this property for multiplier ideals in coordinate rings of smooth complex projective varieties. And Takagi and Watanabe in 2004 proved that this is true for complete ideals in two-dimensional regular local rings. Hubel and Swanson in 2008 proved this for generalized monomial ideals in regular domains. So when they are generalizations of regular system of parameters in regular local ring, one can have a regular domain and take and define an analog of regular system of parameters. And they proved it for monomial ideals in such system of parameters. The subadditivity property, as I said, is used in proving following types of results. Take an ideal which is unmixed of height h in a regular domain. Then the hn symbolic power of I is contained in In for all n bigger than or equal to 1. Yeah, I have not studied how this connection is made, but I am trying to understand how this uniform property of symbolic powers follows from the adjoints. So that shows that it's an important problem to settle in the general case. But as far as I know, the adjoint of Ij contained in product of the adjoint is open for arbitrary local rings or regular domains. Yeah. Right. So now, so this is my humble contribution with Dan Katz and Vijay Kodialam. That we are, and Claire and Saimpriya, that the subadditivity problem and the Lipman's conjecture, they are actually interconnected. So I want to show this connection in dimension 2 regular local ring, and hopefully this connection may survive under some conditions in arbitrary regular domains. So the main result here that we use is take a complete M primary ideal of two-dimensional regular local ring. Then the co-length of the adjoint is multiplicity of I minus length of R mod I. So this result, let's see how this comes. So take a quadratic transform of R and look at the algebraic degree S mod ms colon R mod m beta s. Now use the Hoskin-Deligne formula and the point basis of adjoint. Point basis of adjoint was found by Lipman. Using the point basis of I, one has the point basis of adjoint of I, and therefore Hoskin-Deligne formula can be applied to calculate multiplicity of I and the co-length of I by Lipman's formulas, and it is simply sum over all the base points of order of is square beta s minus the binomial order of is plus 1 choose 2 beta s. And using the point basis of adjoint, one can easily see that this is the co-length of the adjoint of I. And so we have this connection between I and adjoint using the co-length. This is in the joint paper with Claire and Saint-Priya. Take two complete ideals which are M primary in a two-dimensional regular local ring. Then for all R and S bigger or equal to 1, A to the and A comma B is a joint reduction. So A to the R times adjoint of JS plus B to the S times adjoint of IR is adjoint of the product. Now, so this implies the subadditivity problem, and it also implies the Lipman's conjecture. So using joint reduction, we have this very simple formula for the adjoint of products. And to prove this, we simply use this relation between the co-length of adjoint of I and co-length of I. And so now take IRJS. And so the length of R mod adjoint of IRJS is multiplicity of IRJS minus length of R mod IRJS. Now the length of R mod IRJS is, we use Bhattacharya function, and the multiplicity of IRJS can be expressed in terms of mixed multiplicities. So we do that now. So take a joint reduction of I and J and use the fact that A to the R, B to the S is a regular sequence. The direct sum of R mod adjoint of IR and R mod adjoint of JS is isomorphic to the module ARBS quotient by AR adjoint of JS plus BS adjoint of IR. So there's a natural map between left-hand side and right-hand side, and that natural map by properties of adjoints in dimension 2 regular local ring says that this is an isomorphism. So therefore, we can take the co-length length on both the sides. So length of R mod AR adjoint of JS plus BS adjoint of IR is the length of adjoint of IR plus length of adjoint of JS. And this we have to take the length of ARBS, but AB is a regular sequence. So the length of R mod ARBS is RS times the multiplicity of A comma B. But the multiplicity of joint reduction is the mixed multiplicity. There is only one mixed multiplicity in dimension 2, and that mixed multiplicity is the multiplicity of every joint reduction by theorem of Ries. And therefore, we have this formula for the length of R mod AR adjoint of JS plus BS adjoint of IR. And so we use Lipman's formula for mixed multiplicities of complete ideals and Ries mixed multiplicity theorem to see that the mixed multiplicity can be obtained from the point basis. It is the sum of order of IS square plus order of JS square times beta S over all points, all the base points of I. And so if you put together this formula and simplify, then we get this equation that AR adjoint of JS plus BS adjoint of IR is adjoint of IRJS for all RS bigger or equal to 1. Now we remember Ries-Sally theorem, where they proved that the integral closure of the product of D ideals is contained in every joint reduction. I wonder whether this equation has a similar result for adjoint. That is, if you take adjoint of product of D ideals, is it contained in every joint reduction? Yeah. So the subadditivity of adjoint now just follows. You just take R equal to S equal to 1, and you have a more precise formula than the subadditivity, that adjoint of IJ is A times adjoint of J plus B times adjoint of I, and therefore it is contained in the product of the adjoints. And if you take I equal to J, then Lipman's conjecture follows. So the two conjectures actually coincide more or less in dimension 2 regular local ring, but maybe in the higher dimension they are different conjectures. Yeah. Okay, so how much time I have now?
About 20 minutes, yeah.
Okay. All right. So now in the last part of the talk, I want to talk about normal Hilbert polynomial and show the connection of the coefficients of normal Hilbert polynomial of a monomial ideal with adjoint of a monomial ideal. So take a M primary ideal of an analytically n-ramified local ring of dimension D. Rees showed that the normalized Rees algebra is a finite module over Rees algebra of I. And actually it characterizes analytically n-ramified local rings. You can see a proof in the book by Craig and Irena that the finiteness of normalized Rees algebra over the Rees algebra of I implies analytically unramified property of a local ring. The normal Hilbert function, because of this fact, the normal Hilbert function length of R mod in bar is given by a polynomial of degree D for large n, and we call it normal Hilbert polynomial of I. And as usual, we write it in terms of binomials, but the coefficients will be written as bar to denote that it is for the integral closure. And these are called normal Hilbert coefficients. Here is the result. I want to give a sketch of a proof. Take a zero-dimensional monomial ideal in polynomial ring over a field. Then the normal Hilbert polynomial of a monomial ideal has zero constant term. And so there is a last non-vanishing normal Hilbert coefficient, namely E bar D minus I, and that happens to be the length of R mod adjoint of I. So this is the connection of adjoint with the coefficients of normal Hilbert polynomial. And there are other connections. In fact, all the coefficients of normal Hilbert polynomial can be written in terms of lengths of adjoints of powers of an ideal I. But it's a little difficult to write down all these things. So I will only talk about this. But all coefficients can be expressed in terms of the lengths of adjoints of powers of I. All right, here is a sketch of a proof. Take the Newton polyhedron of this monomial ideal, and Tessier proved that the integral closure of In is generated by monomials xu, where u is a lattice point in the n times q. So take the dilation of q, multiply. So take the Minkowski sum of q n times, and take the lattice points in this Minkowski sum. That is also a polytope, and take the monomials corresponding to the lattice points in NQ, and they generate the integral closure of In. And therefore, the normal Hilbert function of I, which is length of R mod In bar, is the cardinality of the lattice points which are outside n times q. Yeah. So that's a finite set. You can sort of visualize it. Take in the plane. Take polynomial in two variables, and then the Newton polytope is a infinite convex set. But its complement in the first quadrant will have lattice points, and the number of lattice points in the complement of the first quadrant of the Newton polytope is exactly the length of R mod In bar. Okay, so we use this result of Tessier, and so we can calculate this by imposing a cutoff so that we get compact polytopes. Newton polyhedron is not compact, but as far as computation of the complement of the Newton polytope is concerned, we can sort of create two compact polytopes and still calculate the length. Fix a minimal generating set. So every monomial ideal has a unique set of minimal generators of monomial generators, and you can take those minimal generators of monomial ideal and let n be the natural number strictly greater than all the exponents occurring in the monomials in S. And now imagine a hypercube where the points extend up to n in every direction. So take that hypercube, and that hypercube will contain the complement of the Newton polyhedron of this monomial ideal. And so therefore we can use this hypercube to calculate the normal Hilbert function. So this is the hypercube, convex hull of all the points x1 up to xd, where xi's are in 0, n. So n is the max of the exponents of the monomials occurring in the minimal generating set of I. So take the intersection of this hypercube with the Newton polytope of the monomial ideal. Now this is a compact set. P is this compact set, and we use this compact set to calculate the normal Hilbert function. So if P is any compact convex integral polytope in Rd of dimension k, then the number of lattice points in the nth dilation of P is given by what is called Erhard polynomial, EPN, for every n bigger than or equal to 0. So you dilate P by n, take NP, and then inside NP, look at the lattice points. So as n grows, the number of lattice points also grows, because many lattice points inside P may have rational coordinates, but when you multiply this by n, more and more lattice points will occur in n times P. And Erhard polynomial measures how this number of lattice points grows with n. So EPN is number of lattice points in n times P. So one proves that the degree of EPN is k. This is due to Erhard. And if you put n equal to 0, of course, we get only the origin. And therefore, the Erhard polynomial at 0 is 1. And we have a beautiful reciprocity, Erhard-McDonald reciprocity, which says that this polynomial, Erhard polynomial, if you put n equal to -1, then EP -1 is -1 to the power k. K is the dimension of the polytope times the cardinality of lattice points in the interior of P. So one can count lattice points in the interior using the Erhard polynomial of P simply by computing at the negative values of n. So this Erhard reciprocity is used in settling many conjectures. We use this Erhard reciprocity to get the result about adjoint and the connection between normal Hilbert polynomial of I and the lengths of the adjoint. So take a lattice point in ND that is not in the Newton polytope of I, but the way we have constructed our hypercube, these lattice points which are not in Q, they are inside this hypercube, because it's a large body which contains all the extreme points of the Newton polytope. So lattice points in ND that are not in NQ are exactly the same as those in NC which are not in n times P. So I wish I could draw some figure, but you can take the plane monomials in two variables to see what I'm talking about. And so using this fact, the normal Hilbert function is the difference of the Erhard polynomial of this hypercube and the Erhard polynomial of the Newton of this polytope P. Remember, P was the intersection of the hypercube with the Newton polytope. Okay, so the Erhard polynomial is associated with compact polytopes. So therefore, we take this difference of these two Erhard polynomial, and that is the normal Hilbert function of I. Now, for the cube, Erhard polynomial is very easy to calculate. For a polytope, it may be hard to calculate, but we have this difference, and all that I'm concerned is understanding the last non-vanishing coefficient of the normal Hilbert function. So write for integral polytope, we want to write the Hilbert, Erhard polynomial the way we write Hilbert polynomials. Usually in the Erhard polynomial community, the Erhard polynomial is written in terms of powers of n. And the coefficients of powers of n, they have geometric significance. But here we want to write EPN in terms of binomials so that we can compare the Hilbert polynomials written in terms of binomials. Setting n equal to 0, because EP0 is 1, we get that the last coefficient is -1 to the power d. Now use this equation h bar in equal to ECN minus EPN to see that the ED bar of I is 0, because both the coefficients are equal of ECN and EPN. So the last coefficient is 0. That is well known, but this is how we obtain that the last coefficient of the normal Hilbert polynomial of I is 0. So the question arises, what about the next coefficient, ED minus 1 bar? And so if you put together the two Erhard polynomial, ECN minus EPN, and the binomial formula for the normal Hilbert polynomial, you can see that the ED minus 1 bar I is the difference of ED minus 1 of C and ED minus 1 of P. And now from these expansions, we can, this comes out by comparing the Erhard polynomials. But Erhard polynomial has interpretation using the Erhard-McDonald reciprocity. If you put n equal to -1, so we put n equal to -1, we get EC minus 1 minus EP minus 1. And if you put together Erhard reciprocity, you will get -1 power minus d, ED minus 1C minus ED minus 1 P. Okay, and so therefore we get this formula for ED minus 1 bar. And now it's a matter of computing EC minus 1 and EP minus 1. C. So if in general, if P is contained in C are both d-dimensional polytopes, then interior of P is contained in interior of C. And ED minus 1 bar, I counts the number of lattice points by this formula. ED minus 1 bar counts the number of lattice points in the interior of C, but not in the interior of P. Yeah. So EC minus 1 and EP minus 1, we interpret in terms of Erhard reciprocity, in terms of lattice points in the interior of C and P. And so that gives us the count on ED minus 1 bar as a count of number of lattice points in the interior of C, but not in the interior of P. So look at the points, lattice points, which are interior of C, but not in interior of P. And therefore, the ED minus 1 bar is the cardinality of X. Okay. Now let Y be these lattice points which have positive coordinates. So I use P. This is not projective space. This P is set of positive natural numbers. I mean positive integers. So V belong to PD. All coordinates of V are positive, and which is not in the interior of the Newton polytope. We are interested in counting these to calculate the normal Hilbert polynomial. We'll show that X is actually equal to Y. So this Y relates with the adjoint, because to get the monomials in the adjoint, I have to add the vector 1, 1, 1 and get inside the interior of the Newton polytope. So we use that interpretation of adjoint. And maybe I will skip these little details. And yeah. Okay. So this is a little difficult to see without pictures, and I didn't know how to draw all these pictures. So the takeaway is that the normal Hilbert polynomial of Y has these coefficients, and all the coefficients of normal Hilbert polynomial can be computed if you know the adjoint of I and the powers of I. Okay, so I can stop here, Bernd, and take some questions.
Thank you very much, Jugal. Are there any questions?
I have a couple. Jugal, can you hear me?
Yes.
Oh, that was a really nice talk. Thank you very much. And that last result is very thought-provoking. But I had a comment and a question. So the comment is back to Dale's work. I think Moriyama may have some recent papers where he proves Kodaira type vanishing in the analytic and complete cases, which maybe would do that characteristic zero part of Lipman's conjecture, which Dale used the Kodaira vanishing type results for. And I don't know his papers. I just know they exist. And Carl, you are nodding your head. I don't know if that's.
I would agree. Takumi Maruyama proved Kodaira vanishing for, I think, like resolution of singularities over a ring with a dualizing complex.
So
is
this
one
is any characteristic or
no. Characteristic zero, of course. So Q schemes.
Characters
Okay.
is just to get
Yeah.
out of essentially a finite type.
Yeah, I was thinking actually when hearing Jugal's talk that maybe all you need is like a regular ring containing Q. That would be enough. Or I forget what the original category was, but a ring containing Q is not the essentially a finite type part. I would expect could be removed.
Yeah, so if you can pass to a completion, then Kodaira just is fine or whatever, basically.
And the questions I had, I was thinking with your monomial ideals, that was really beautiful. A lot of ideals, you can kill a general linear form maybe and get a monomial ideal sometimes. So I was curious what's known about, for instance, if you take the adjoint of I colon a general linear form, how does that relate to the adjoint of I colon that linear form? Do you know? Are there any theorems?
Lipman in his paper, I think in arbitrary regular domains, he has stated many colon properties of adjoints. So I think he proves that adjoint of I times j colon j is adjoint of I.
I see.
He has several such formulas relating colon properties. Yeah.
Because it might be interesting to think about killing general linear
Right, but your question is about taking colon with respect to some general linear form.
Yeah.
So I don't see that in his formulas.
That was all.
Yeah.
Thank you for that.
So it may be worth understanding that. Yeah.
It really took me back
So
to Purdue.
one problem that I find
First
in
time.
understanding adjoint is that there's no induction argument. I mean, how does the adjoint behave when you go mod? This is what you want to understand. That how does adjoint
Well,
behave
not
when
only
you go
mod,
mod a
but it's
general
colons.
element?
Yeah.
Colon, right. Yeah.
Professor Verma?
I mean, complete ideals, one can tackle them by going to general extension and take a general element. The complete ideals, at least the powers of complete ideals, they behave very well by Ito's work. But the techniques that Ito employs, I wonder whether they are valid for adjoints of I. That is, if you go to a general extension of the ring and take a general element in the adjoint, a general element in I, and go mod that general element, how does the adjoint behave? Is it same as is it just equal to taking the adjoint and go mod the general element?
Actually, this isn't quite this, but there's a paper by Tessier where he considers this type of problem. It's all for analytic local rings, but he shows something like if you have a complete ideal and then you mod out by a general element of the ideal, then it stays complete.
Right.
Which is sort of in this direction anyway. Maybe something like this holds. I don't know that.
Yeah, whether the adjoint also specializes this way.
Yeah.
Professor Verma?
Yes. Yeah.
Hi, this is Rahul. I actually had a little result around Professor Lipman's conjecture. I proved that conjecture or the Cutkosky vanishing basically in dimension 3 in all characteristic, including mixed, which gives me the adjoint ideal relation as well.
Oh, that's interesting. Is it published?
Yeah, it is in archive. Here is the link.
Okay.
Yeah.
Okay. Yeah, it's nice to know. So this is a characteristic free proof.
Yes, sir.
I see. Okay.
I shared it in the chat.
Okay. Yeah. Okay. But it's only in dimension 3 regular domains.
Sorry, R is a rational singularity. Yeah, that was my assumption.
I see. So I wonder how adjoints are defined in rational singularities.
So
in the same way.
resolution.
Same way
Yes, exactly same way, sir.
Yeah. Somehow Lipman always assumes the ring is a regular domain when he defines adjoints. But of course, the definition makes sense in terms of the Jacobian ideal.
Yes, sir.
Yeah.
Are there any other questions?
I have one more question for Jugal. That your last result, you had this E sub D minus
Yeah.
1 bar of I is the length of R mod the adjoint of I for monomial
Right.
ideals. If you
Yes.
look at, you remove the monomial condition, you could view this as sort of a specialization. You can specialize to a monomial ideal. Is there any possibility you could use this to get some sort of inequality?
You mean ED minus 1 bar less equal to length of R mod adjoint of I or something like that?
Yeah, something like that. Yeah.
I would guess that if you take M primary ideal in regular domain in any dimension and impose the condition that the normalized Riesz algebra has rational singularities, such a result should be true. Because the normal Hilbert polynomial is controlled when the pros of the normal Riesz algebra has rational singularity. Because lots of Schiff cohomology modules will vanish, and that has effect on. I think it will imply that the normal Hilbert function is normal Hilbert polynomial in arbitrary regular domains. If the normalized Riesz algebra is Cohen-Macaulay, it will retain that property of monomial ideals. You certainly need this fact that normal Hilbert function is normal Hilbert polynomial right from n equal to 0 onwards. And that property is implied by rational singularity property. So at least this condition may be needed, and we may have something like this in arbitrary regular domains under some conditions on the normal Riesz algebra.
Okay, if there are no more questions, so let's thank Jugal for the great talk. Thanks very much, Jugal. It was a wonderful talk.
Thank you, Bern. And thank you everyone for showing up. Yeah.
Thank you, Jugal. Thank you.
Bye-bye.
Bye.
Hope to see you back sometime.